Welcome, everyone. We are the Ideas Clinic Industrial Automation team. My name is Jason Gill. I'm an electrical engineering student.
My name is Steven. I'm in 2A Mechatronics Engineering.
Hello, I'm Calvin in 3B Mechanical Engineering.
And I'm Ben, and I'm also in 2A Mechatronics Engineering.
So the goal of this industry automation project is to bring in a real factory setting into the classroom. So obviously we can't bring in real life conveyor belts, robotic arms into the classroom as they're too large. So we decided to make a smaller scale version using professional equipment and leave space for students to add their own creativity and innovations to these devices. What we've made is a set of conveyor belts, robotic arms, and control systems that can act as versatile teaching tools for simple building and design concepts, as well as math and robotic kinematics, as well as a real-life IoT experience for students in the classroom. A quick overview of this project: we've partnered with Brock Solutions, a real industry automation company, to help us with this project, so we can get a view of what things are really like in the industry and how we can closely replicate it in the classroom on a smaller scale. So we use PLC control systems, motion control, factory planning, data management, as well as conveyor belts and robotic arms to replicate what goes on in an industrial automation site.
The conveyor uses a whole slew of sub-assemblies, which might be found in real-life examples of industrial automation. On the left, we have pictures of such subsystems from our own design, and on the right, we have pictures of these same subsystems being used in real-life industry examples. We have the PVC belts with lacing, diverter assembly, the drive assembly, and control panel. Here we have some videos of the conveyors working. So as you can see, the box is brought from one conveyor to the next conveyor in the system. From there, it passes through some sensors. Although in this video, it is being controlled by a user with the control panel. And then the diverter arm is activated and it pushes the box from the conveyor onto the buffer area or waving area, where it could then be picked up by the robotic arm, which we'll be talking more about after, and brought between platforms. Here's another video from the perspective of the camera, which could be used to process a barcode or a symbol placed on the box to identify its contents. Here is an image of the completed assembly. As you can see, it consists of 4 conveyor belts attached in tandem, and they could bring the boxes in a loop, where they could then be properly sorted and brought to the buffer area by the diverter arms, and then moved accordingly by the robotic arm.
So naturally, after diverting a box onto the buffer zone, it's important that you're able to remove that box from the buffer zone and move it elsewhere in the factory. In the industry and in our industrial automation project, we chose to use a robotic arm to accomplish this. And this robotic arm uses many of the same control strategies and components as real robotic arms, including microcontrollers, belts, pulleys, bearings, and gearboxes, and stepper motors in our case. So our robotic arm has 3 degrees of freedom, meaning that the end effector and the gripper can move up and down, forwards and backwards, and left and right. The gripper can also rotate to better grab onto boxes and can clamp down and grab the boxes to move them. The major project of the fall term was version 2 of the arm to improve the precision, stiffness, and weight. To control the arm, we're using a X-Nucleo driver board, which very precisely drives the stepper motors. And we're talking to that board using SPI and serial communication. At right, you can see a video of the arm moving, picking up a box and moving it to another position, similar to the function it will perform in the overall assembly.
As for the control system for this robotic arm, we're using a Nucleo STM32 microcontroller because this one is classroom tested in MTE325. We know how it works and we've seen students use it before. This allows us to give students the opportunity to program inverse kinematics onto the robotic arm themselves and change up the code to add precision or whatever they need to their own systems. We use this controller to also communicate with our PLCs, and this brings a whole new set of challenges for students to overcome. To speak more on those PLCs, we're using Opto22 industrial use PLCs. We use a Groove Epic as a main control hub and a Groove Rio as the remote I/O module. These two communicate on the cloud via MQTT, and they can allow students to remotely create code that will control the conveyor systems and the robotic arm all from one system. And this is the potential for large communication networks to create more robots, more conveyor belts, and a larger network of different devices that can add to the complexity of this project.
While the conveyors and the robotic arms replicate the functionalities and the sensor suites of their respective real-world components counterparts very well, however, in order to understand how these individual components really power the modern industrial applications, the management of the underlying communication infrastructure and architecture is equally as important. This is especially true in recent years because the logistics and data generated by an entire facility is valuable for analysis like optimization and other big data applications. This is why we strive to bring the state-of-the-art technologies like computer vision, edge-of-the-cloud computing, and industrial Internet of Things that are used in the industry into classrooms, so that students can gain an appreciation and understanding of how they work, then apply them in their co-op positions. Now let's start with how the basic functions are performed in such paradigms. Our application of industry-grade PLCs like the Groove Reels replace the role of traditional microcontrollers due to their high current GPIO, high-level programming interface, and general reliability and robustness. This means that they can control high current components like motors directly without external MOSFETs or relays, and that they have a web interface for both inspection and programming. So you don't need to stare at some C code base in a legacy IDE to turn on a motor, for instance. It also means that they have built-in IIoT capabilities, which greatly improves the scalability and makes management a breeze compared to traditional serial-only infrastructures. We still use an STM32 for computing inverse kinematics and controlling subsequent stepper motor movements due to the work done before this iteration of the project. But this just goes to show how these industrial PLCs are a neat drop-in replacement when upgrading existing infrastructure without starting over, since they can talk to existing legacy controllers via serial protocols. Both the conveyor and the arm can be controlled by the NVIDIA Jetson Nano, which reads labels on the conveyor payloads like colored symbols or letters using both an RGB camera and a depth camera, and then it activates the diverter and sends them to the buffer area as desired, along with the information like the coordinates and the height to the reel via IIoT, which is then relayed to the ARM's embedded controller once the package has arrived on the buffering platform. This powerful IIoT technology, which gained a ton of popularity in recent years, enables a single Ethernet connection to perform what took huge bundles of wires before they emerged. So as an example, when the expansion of 10 additional devices is mandated, for example, all it takes is one single networking switch and 10 Ethernet cables instead of worrying about occupying and wiring 10 extra I/O ports from the existing controller, or adding another level to the hierarchy altogether with a new controller. So as you can imagine, this level of flexibility is highly desirable in the industry, and thus it is a key emphasis of this project. The exact IIoT technology we're using is called MQTT, and as you can see in this diagram, Mosquito is a particular open source implementation of MQTT, or the message query telemetry transport, where data can be published to topics that can be then subscribed by other nodes, like aka devices on the network. Redundancy can also be built into the architecture by hosting extra cloud instance brokers in case the main one fails. Now let's examine the role and the purpose of this ignition software that you see at the bottom. It is what's known as a Scada software, or supervisory control and data acquisition software. Due to the web nature of ignition, client devices of virtually all operating systems can act as an administrative portal, or commands can be issued in a database to a database. Where commands can be issued and the equipment status can both be read at real time or to be stored into a database. Needless to say, this logging function is the cornerstone of any management or data science project, not to mention the facility security benefits.
Thank you for listening. That's the end of our presentation. Have a nice day.